Hello viewers, welcome to the another interesting lecture of digital communication. Some of you inquired me about the mathematical operations of the matrices. So in this lecture, we are going to discuss mathematical operation of the matrices and the basic of the matrices. This lecture is totally conducted by Ganon, powered by Wishback. I am Professor Aditya De. So first of all, let us discuss what is a matrix. In mathematics, a matrix, or in plural, matrices, is a rectangular array of numbers, symbols, or expression arranged in rows and in columns as shown in this figure. You can represent the matrix either within a square bracket or within a first bracket. The horizontal lines are known as rows and vertical lines are known as columns. Now, in this case, the m number of the rows and n number of the columns exist. So, the dimension of the matrix is m cross n. Why so? Again recap, because m is the number of the row and n is the number of columns. Now let us discuss the matrix operations. The first operation is addition. The sum of the two matrices C plus D of two m by n matrices C and D is calculated entry-wise. That means in general form, C plus D suffix ij is equal to Cij plus Dij, where I is lies between 1 and m and j is lies between 1 and n. Let us take one example. Say one matrix with 1 3 1 and 1 0 0 as shown in the figure, and another matrix is with 0 0 5 and 7 5 0 is added. Now the result will be, first one is in the first row it will be 1 plus 0, then 3 plus 0, after that it will be 5 plus 1. In the second row it will be 1 plus 7, 0 plus 5, 0 plus 0. So what will be the final result? The final result will be 1 3 6 in the first row and 8 5 0 in the second row. Now let us discuss another important matrix operation, which is scalar multiplication. The product C D of a number C, also called a scalar in the Parallels abstract algebra, and a matrix D is computed by multiplying every entry of D by C. That means in general format, CDIJ is equal to CDIJ. This operation is called scalar multiplication, but its result is not named as scalar product to avoid confusion. Since scalar product is sometimes used as a synonym for inner product. Let us take one example. You take one matrix 1 3 1 and 1 0 0 and multiply it with a scalar 2. What will be the result? In the first row it will be 2 into 1. After that it will be 2 into 3, then 2 into 1. In the second row it will be 2 into 1. After that 2 into 0 and 2 into 0. The final result will be 2 6 2 in the first row, and in the second row it will be 2 0 0. Let us discuss the transpose operation of a matrix. In this case, the transpose of an m by n matrix D is the n by m matrix D to the power capital T, or you can denote it by D to the power TR or D to the power T, formed by turning rows into columns and vice versa. That means dt suffix ij, that means number of rows column will be rows and rows will be column. So it is equal to d of ji. Let us take one example. If the matrix is 1 3 1 and 1 0 0, what will be the transpose? The transpose will be 1 1 3 0 1 0. Now let us discuss in this case, what is the point to be noted? Point to be noted, if you add two matrix, that means C plus D, it will be D plus C. Number 2 point to be remembered, C D whole to the power transpose equal to C D to the power transpose, where C is a scalar quantity. Now, capital C plus capital D whole to the power transpose equal to capital C transpose plus capital D transpose, where capital C and capital D both are matrices. And if within the bracket C transpose to the power transpose, it will be again the original matrix capital C. Now let us discuss the matrix multiplication operation. Here the matrix will be taken, two matrices are taken, A and B. For the matrix A, the elements are A1, A2, A3. After that it will be A4, A5, A6, then A7, A8, A9. For the B, it will be B1, 2, 3, then B4, 5, 6, and B7, 8, 9. If the result of the multiplication is C1, C2, C3, C4, C5, C6, C7, C8, C9, the multiplication will take place in reverse L pattern. This is for your remember. And the resultant will be C1 is equal to A1, B1 plus A2, B4 plus A3, B7. C2 will be A1, B2 plus A2, B5 plus A3, B8. C3 will be A1, B3, A2, B6 plus A3, B9. What will be the case of the C4? Guess? Okay, let us check your answer. The C4 will be A4, B1 plus A5, B4 plus A6, B7. Similarly, C5, C6, C7, C8 and C9. You just do it yourself and check the result as shown in the diagram. Now let us discuss the multiplication in general term. That means a matrix capital A with M cross N dimension and matrix B with a N cross P dimension. So what we discussed earlier, that the multiplication will take place in the reverse L pattern. The resultant of these two matrices will be as shown in the figure. And the resultant matrix dimension will be M cross P. The point to be noted in this case, the dimension of the first matrix is M cross N and dimension of the second matrix is N cross P, as I told you earlier. Hence, the multiplication is only possible when the column of the first matrix is equal to row of the second matrix. The resultant matrix dimension is M cross P. That means row of the first matrix cross column of the second matrix. And you remember that if you multiply the matrix, it is not reversible. That means if you multiply matrix A with a matrix B, it will not equal to matrix B into matrix A. Now let us discuss the submatrix. Let us take one small example. The example is 1, 2, 3, 4, 5, 6, 7, 8, then 9, 10, 11, 12. If you take a subpart of the matrix, it will be 1, 3, 4 and 5, 7, 8. So what is a submatrix? A submatrix of a matrix is obtained by deleting any collection of the rows and or columns. Now let us discuss matrix determinant. The notation is det A for a matrix. It will be within a two-line capital A is equal to A, B, C, D. The result will be AD minus BC. This is for a 2 cross 2 matrix. Now, for a 3 cross 3 matrix, let us take the matrix is B and the elements are A, B, C, D, E, F, G, H, I. What is the result? A, then det E, F, H, I minus B, D, F, G, I plus C, D, E, G, H. What is the result? Try yourself. Okay, let us check our result. It will be A into EI minus FH minus B into DI minus FG plus C into DH minus GE. The points to be noted that determinant calculation is only possible when number of rows is equal to number of the columns. That means for a square matrix. Now let us discuss the minor and the cofactors of a matrix. Consider a determinant delta is equal to A11, A12, A13, then A21, A22, A23, A31, A32, A33. The determinant of the minor m is capital M is equal to capital M11, M12, M13, M21, M22, M23, M31, M32, M33, where capital M11 is equal to minor of small a11 is equal to small a122, small a23, a32, a33. M12 is the minor of a12 is equal to a21, a23, a31, a33. And M13 is the minor of a13 is equal to a21, a22, a31, a32. Similarly, we can find the minors of other element. Using the concept, the value of determinant can be delta is equal to a11 m11 minus a12 m12 plus a13 and m13. Can you represent this determinant in some other way? Yes, you can. This can be represented by delta is equal to minus a21 m21 plus a22 m22 minus a23 m23. This is one way. There is another way. That means delta is equal to a31 m31 minus a32 m32 plus a33 m33. So what we have discussed today? We have discussed the basic of the matrices. Also, we discussed the determinant and the minor of a matrices. Also, we have discussed some basic matrix operation. That's all for this segment. We will continue this segment in another lecture. Thank you, viewers. Bye.